So this is an improved version of lecture 6 by Harvey Friedman, please.
Thank you. Okay, so today we're going to talk about invariant. I do want to change the title slightly. It's not just choice, it's free choice. This is a kind of different style of statement which has its advantages, and invariant maximality has its advantages also. And it looks like a key step. It may be a key step towards further developments, but we're going to talk about this free choice. And then starting in lecture 7, the next lecture, we're going to spend many lectures on the reversal. The reversal is an invariant maximality, but that will automatically reverse the key statements in free choice, because the key statements in free choice will imply invariant maximality in RCA naught. In fact, we'll have a sketch at the end of that. So no new reversal is needed, just the core reversal for invariant maximality. The free choice is proved by the simplest way to prove the free choice is to imitate and lift the proof for maximality using the same large cardinal. All right, so the free choice is somewhat recent. I want to start by reviewing the structure of the invariant maximality. It took a while to settle on this because there are multiple variants, but they have to be grouped and organized in a nice way. So that's what I want to review and talk about that. So there's what I call the lead statements. And these are the ones that one encounters first. So they have to be sort of the so-called best ones or simplest. And there's 6 lead statements. And I took out one. Actually, that was an earlier. It was an earlier version of free choice that we're going to talk about. I pulled it out and replaced it with another statement in the invariant maximality tradition. All right, so we need a new definition for this. We defined what we meant by a root of a 2K dimensional set before. That's what the lead statement, the first lead statement concerns. But this is what's called an ORD root, which is K dimensional. An ORD root, excuse me. I'm sorry. This is an ORD root, which means that every x in S squared is order equivalent to some y in E. Yeah. So this is actually really very much like the almost identical to the root statement, but it's in a different style, which is the style that I use for emulators. So let's review this specifically. So here are the 6 statements. Every order invariant subset in 2K dimensions has an invariant maximal root. That has always been the lead statement. This is the statement that's been changed, and it's influenced by this statement here, which is basically a generalized form of the statement that I used for gifted high school program, the Arnold Ross program, a couple of years back. My lectures concerning the Arnold Ross program, in the order involves program, are on my lecture note website. All right. So every order invariant subset of 2K dimensions has a invariant maximal root. That's the statement that I pick for the general mathematical community. I think this is probably the best, the one that resonates the most. Then there's this one, which also resonates, but is in a more concrete direction. Every finite subset of in 2K dimensions has a invariant maximal ordinate root. And this is really equivalent. These are easily seen to be equivalent, these two. Because order invariant sets are given by finite sets. They have a basis, so to speak. All right. The emulator one is every finite subset has a invariant maximal emulator. In an emulator, any pair from the original finite set is order equivalent to some pair from the maximal emulator. See, you start with a k-dimensional set in emulator form instead of a 2k-dimensional set. All right, then we have every order invariant subset of Q in 2 dimensions has a shift invariant maximal free set, using the notion of free set in a relation. Any 2 distinct elements are not related. And then the clique one, every order invariant graph has an invariant maximal clique. And then finally, a generalization of the root. Every order invariant set has in MK dimensions has an invariant maximal M root, meaning the mth power is contained in the original set. These are the 6 lead statements. I call them the 6 lead statements. And what's new here is that I have an elementary proof that all 6 are proven equivalent over RCA naught. This is new because I had to treat this last one as special. I didn't know whether it had an elementary derivation. And it turns out that it does with a little bit of more effort. I was able to do that. Now there's a parallel set of variants which are weaker when we actually set all the variables to be k. In other words, Q0k to the k, Q0k to the 2k. And here it was 0 and kk, meaning k squared on the top with k root. So it's nice to have a version with just one variable. And we write that as, we write this general class like this: triple x less than 1 shift, triple x less than 1 shift, 1 QV. 1 QV is read one quantified variable. One quantified variable. All right, so that means that we have 12 statements. We have 6 lead statements. We have the one variable version of the 6 statements, so that's 12. And that uses less than 1 z plus shift invariance, which we described a few times in the previous lectures what that means. You shift the positive integer coordinates and leave the rationals less than 1 alone, assuming that there are no other coordinates. All the coordinates are either less than 1 or positive integers. Okay, and this is always within a bounded space. All right. Now we also have 3 additional sets of 12 statements. These 4 sets are referred to as triple x less than 1 shift, triple X less than 1 ORed, triple X less slash lower shift, triple X slash lower ORed, lower order invariant. And these are based on four different notions of invariance. So you have a total of 48 statements. Now, each of the group of 12 are provably equivalent by elementary argument in RCA naught. Just like the original 12, based on the 6 leads, are provably equivalent in RCA naught by elementary arguments. Each one of these 12 are, but you don't have any elementary proof of the different 12 because they're based on different invariance notions. And the strongest one, the strongest invariance notion is lowered or lower order equivalent. Now, we will have that all 48 statements are provably equivalent in WKL naught at least. We will have that by passing through our reversal because the strongest of all 48, this is the strongest of all 48. And that's actually quite easy to see that that's the strongest of all 48. And then the weakest of all 48, which we'll discuss in a second, the weakest is reversed. That's what the reversal is from lecture 7 through the end, or essentially the end of the series. So we do get that all 48 are equivalent to con SRP over WKL naught. Now, actually, in the book, now we finished proving invariant maximality statements with large cardinals in the previous lecture, but in the book, I'll actually simplify things slightly by using this version, because I said that all of them are equivalent. All of them are equivalent. All the 12 are equivalent when I use lower Z plus order invariance. So what you'll see in the book is a proof of this from large cardinals. All right. For the reversal, we actually use well, the weakest of the 4 invariance notions is less than 1 comma Z plus shift invariance, i.e. these are the weakest 12. And actually, with one quantified variable, these are the weakest. And they're implied by all 48. For the reversal, we use something in here. I'll describe that later for the reversal, starting next lecture. We don't have, of course, elementary proofs of equivalence when you change the invariance, as I said. But this is the weakest invariance. So all 48 statements are provably equivalent to con SRP over WKL naught. All 48 statements, incidentally, are implicitly pi01 via the Gödel completeness theorem. And that's a nice undergraduate math logic exercise. Now, more specifically for the reversal, we'll actually be using this particular one of the 48. Invariant maximality clique less than 1 shift 1 QV. Every order invariant graph on Q0K to the K, see the same variable, has a less than 1 Z plus shift invariant maximal clique. All right. So now I want to turn to my main topic for today, which is invariant free choice. So instead of using sets in the conclusion, we're going to use functions. This has some advantages, disadvantages, however you want to look at it. And we also want the advantage, actually, of just using one space. q to the k. So this is in some ways nicer, although invariant maximality has its also advantages. All right, so we'll work in Q instead of Q0n, and we'll use functions rather than sets for the conclusion. The invariance condition asserts that certain simple, so the invariance condition takes on a somewhat different flavor. It asserts that certain simple partial functions, this double dot means partial functions, that certain simple partial functions are isomorphisms, I don't mean this, are self-embeddings. Are self-embeddings of the concluding item, the concluding function. The richness of the self-embeddings corresponds to the level of set theory required to prove the statement. Okay. Now, these new statements are proved in the same way that we prove statements in invariant maximality with the same large cardinals. So we're still doing everything in WKL naught plus con SRP, or if you like, in the system SRP plus. Now, statements in invariant free choice are reversed by reversing them to statements in invariant maximality, which are turn being reversed to con SRP in this lecture series, starting with lecture 7. All right, so let's get to it. Let's talk about what a choice function is and what a free choice function is. So let R be a relation on X. F is a choice function for R if and only if F maps X into X, and for all X and X, X are F of X. Now, of course, there may not be a choice function in this sense because the relation might not be total. F is a free choice function for R, if and only if it's a choice function whose range is free. F is a free choice function if and only if it's a choice function whose range is free. Note the definition of free choice function does not directly involve any maximality condition. It may be somewhat surprising, but the strong connections, but there's an implicit maximality you can derive in here without talking about it. Another advantage. Okay, the strong connections with maximality are seen by theorem 1 and 2. So there's some interesting facts about free choice functions and also their relation to maximal free sets that is pretty interesting. So the first theorem is this: if I have a free choice function, the range is a maximal free set. If I have a free choice function, the range is a maximal free set. Also, F is idempotent. And the range of F is the set of fixed points of F. All right, so this is proved pretty elementarily. So if I have the range is F free by definition, of course, as R free, because the range is that's the definition of being a free choice function. The range is free. Now the question about maximality. So if I have something outside the range, then I must have X R F of X by the definition of the definition of a choice function. I must have X R X, and X must not be F of X because it's outside. So hence the range of F union X is free by definition of free. Now, since FFX and FX lie in range F, and FX is related to FFX, we have F of X must be equal to F of X by the freeness of range. This verifies that F is idempotent. i.e. every element of range F is a fixed point of F, another way of saying the same thing. And obviously every fixed point lies in range F. So we verified that range of F is a set of fixed points of F. All right. Now, theorem 2 actually gets our hands dirty. That's some very nice properties of free choice functions. Now we get our hands dirty and actually tell you exactly what the free choice functions are and how to build them. So you can see that the extremely close relationship. It's just really a maximal free set. A free choice function is really a maximal free set with extra structure. That's really what it is. All right. Now, the only interesting relations we want to consider are ones where we want to all right, I'm not saying that's a little too strong. The relations we want to consider are reflexive and symmetric. The reflexivity is needed so we do have some freedom to obviously make a choice function at will, namely the identity function. But the identity function is unlikely to be a free because that would mean that any two points would be not related. So let R be a reflexive symmetric relation. The free choice functions of R are the functions obtained by first taking any maximal R free set S and defining F to be the identity on S, and for X outside S, defining X to be something related to X that's inside S. Very simple idea. That's necessary and sufficient. That's exactly what they are. As a consequence, a free choice function for R exists because you can always get a maximal free set because it's reflexive. You can always get a maximal free set. Well, you have to, then you get a maximal free set, and then you have to make that function, define that function in the way that I described, which obviously can be done. It's just choice. Of course, we're going to be interested in the case only when X is countable. So the choice is RCA not kind of thing. All right. So let R be given reflexive symmetric, and let F be a free choice function for R. Then the range is a maximal R free set. We prove that in theorem 1. And so we use that for S, and we define F to be the identity. And for each X not in range F, XR F of X can be chosen by the definition of free. And I think, there I need symmetry also. Maybe I said it in the wrong place or need it in both places. You need that R is symmetric. Conversely, let S be maximal R free set where F is the identity on S. Sorry, that was the necessary thing. Then for each X not in S, X R F of X must be picked. And that you can do by symmetry. So let F be a choice function for R. It's obvious that range of F is S. Hence, the range of F is R free, and so F is a free choice function for R. Yeah. Oh, a free choice function for R exists because you can always get a maximal R free set by Zorn, or by a greedy argument, sequential greedy argument if it's in the countable case. So we'll be exclusively using order invariant reflexive symmetric relations. And now what we want to do is impose various conditions on a free choice function f from q to the k into q to the k. Now, before getting into the isomorphism conditions, we start with limitness, with another kind of condition, limitness. Okay, a function f from q to the k into q to the k is limited if and only if for all x in q to the k, the max of f of x is less than or equal to the max of x. Max of f of x is less than or equal to max of x. Now, do we always have a limited free choice function? The answer is obviously not, because constant functions can't possibly be, constant functions cannot possibly be limited, because we go to minus infinity. So in dimension k, consider x r y if and only if x is not equal to y. This is an error. I wanted to show you the constant functions. Okay, so this is, because this is not reflexive. Yes. Let x r y if and only if true. Okay. Sorry. The free choice functions are exactly the constant functions. Yeah. Because any two elements have to be, because the range has to be free, so they can't possibly have more than one element. That's what I want to say. So how about this? Let R equal okay. That's what I meant to say. That's reflexive and symmetric. The free choice functions are exactly the constant function. Yeah. Okay. But let's see how we can get some limitedness. So we can't get limitedness. We can't get it limited, but we can do this. Let E be a set of rationals. Then F is said to be E limited. Yeah, I had changed the terminology. E limited. If and only if whenever max of x is less than or equal to P in E, we have max of f of x less than or equal to P. You see what that means? So we just have these special points, namely E is a set of special points, and we have the limitedness with respect to those special points only, right? And so now we have a template. Suppose E is a set of rationals. Every reflexive symmetric order invariant relation on Q to the K has an E-bounded free choice function. And we want to know when this is true and when this is false, no matter what E is. And I think I've solved this problem. It does need some more checking. So you can use E with this E limited. You can use E limited if and only if for every X in Q with minus infinity added, there exists P greater than X such that E is disjoint from some XP. Interval. I just want to make sure I'm not talking about ordered pairs. Interval. There exists P greater than X, such that E is disjoint from the interval. Okay. Yeah. I think that's necessary sufficient for this, with a proof in RCA naught. No, with a proof in yeah, let's think about this. Yeah. With a proof in ACA. No. All right, I think a proof can be given in ACA, but I'm not 100% sure of that. So it's something else to look at. Actually, I don't believe that. Interesting. Oh, yeah. Yeah, that can be embedded. Yeah. Okay, I think the proof can be done in ACA. So this needs some more work, but I'm pretty sure I'm on the right path here. All right. All right. Every reflexive symmetric order invariant relation has an n-limited free choice function. So that's the first result, positive result in directly in invariant choice functions. Every reflexive symmetric order invariant relation on Q to the K has an n-limited free choice function. And for this, we build a tower of free choice functions uh, for for restrictions of R. So there's no problem defining what we mean by free choice functions if I'm working on instead of minus infinity to infinity, I'm working on minus infinity to t. It doesn't make any difference. The definitions are the same, but relative to the space. So we build them in a tower. You need an extension theorem, then you can always extend a free choice function to a bigger space. If you have a reflexive symmetric order invariant relation. Yeah. Now you take the union and you get an n-limited free choice function for all of R. Now we did something like this in invariant maximality, if you remember. We did a tower, and we remarked that we were getting into successive jumps, in the proofs, and that's exactly what happens here. But now for the self-embedding. So that's the limitedness, but now we want to talk about the self-embeddings. So a self-embedding of a function from Q to the K into Q to the K is an H from Q to the K. It's actually just a partial isomorphism of the structure QF. And I just wrote it out because remember, let's be a little careful. This is not an isomorphism, it's a partial isomorphism. It's partial. Okay. So whenever things are going to be defined, you have that the function is invariant. In other words, you change these materials and you still get the function relation. So this is a kind of invariance, that's very familiar. I mean, obviously, more people work with isomorphisms that are total. This is partial than they do with partial, but this is still common. All right. Now, the end shift of a function is just f of n equals n plus 1. That's called the end shift. It's only defined on n. And then we have the following theorem. Every reflexive symmetric order invariant relation on Q to the K has an n-limited free choice function, self-embedded by the end shift. Okay, we want n-limited and self-embedded. And this is provable in some extension of ACA with omega jumps, ACA plus. Now, the way this is proved is, again, it's similar to some stuff we did with invariant maximality. Let F be a n-limited free choice function. By the infinite Ramsey theorem, we can find, so we just take an n-limited free choice function and we do some surgery on it to get what we want. We find increasing natural numbers such that for all which are basically indiscernibles for the function. This comes from being indiscernibles. This is a special case of infinite Ramsey's theorem. All right. Now we've got what we want, except that instead of the shift, mapping 0 to 1, 1 to 2, 2 to 3, and so forth, we're mapping B1 to B2 and B2 to B3 and B3 to B4, even though this is skipping by more. I mean, we're adding more than one each time. We're skipping over numbers, right? But then this whole problem, this whole setting is purely order theoretic. Everything about this is order theoretic. So we can just make an order isomorphism, this time total, from, we can make an order preserving bijection from Q onto Q, sending each BI to I. And this sends F to an n-limited free choice function for R, which is also n-shift self-embedded. See, we already know that we're going to retain the limited nature of this because these B's are in fact from capital N. We always had n limited. Okay. So that's how that's proved. So now we want to get into the independent statements, the strong statements. So as usual, we introduce parameters. So the way these parameters work here is we look at the less than, I call it the less than 0 n shift. The less than 0 n shift is the function of, yeah, this should be, this is partial, right? The function from n union q minus into n union q minus, which is the n shift on n and the identity on q minus. Yeah, this is already set up nicely. Yeah, so this is fine. Yeah. So the isomorphism is actually a mapping from n union, the negative rationals, into itself, which is the n shift on n and, adding 1 for the elements of capital N and the identity on the negative rationals. All right, so now we have our lead statement, our main statement in invariant free choice. OI, meaning order invariant, free choice, n limited, less than 0 n shift. Well, yeah, I used to write this in the invariant maximality without a comma because it's the title of the statement. Yeah, so you do that. All right, every reflexive symmetric order invariant relation on Q to the K has an n-limited free choice function self-embedded by the less than 0 n shift. This thing up here. This is proved using kappa cross Q01 without, you have to throw out the left endpoint, because remember, this is going to become, after downward Scola-Lowenheim theorem, this is going to become q to the k eventually, instead of, it's going to become q. So we want to make sure it's dense without any endpoints. Kappa is a large cardinal, as we did before in invariant maximality. Now, if you remember, we did this with a little bit more complicated space. If you remember, we had a point on top, but that more complicated space had only one purpose, if you remember, namely that we want to make sure that we've got the right level of the subtle cardinal hierarchy, if you remember, for the statements. So in dimension 2, if you remember, we wanted to prove things in Z3. That's why we did that extra step. And I did want to start with things that you could prove. So there's a similar treatment here. If the dimension is 2, that we can actually use a little more complex space. And also we can get more accurate proofs, reduce the level of subtlety needed if we do it more complicated. But this is the most straightforward way. This is easier. Okay. See, this proof already is going to require a large cardinal in dimension 2. But all right, so let's move on here. So what about the reversal of this statement? Well, from this statement, we prove this statement. From that statement, we prove invariant maximality. And this shouldn't surprise you, because we already remarked things that the free choice functions are related to maximal free sets. They give you a maximal free set. Their range is by definition a free set, but you can prove that the range is maximal free. That's what we did earlier today. All right, so how do we show that this statement, it follows from the free choice statement? So let R be an order invariant relation on Q0 n to the k. And there's no harm in taking the reflexive symmetric closure of R. That doesn't change the free sets, by the way. Same free sets. Let F be given by the statement we're trying to reverse here. Then the ranges are star free, right? Because we made our reflexive and symmetrics, we can do this, and hence are free. In fact, the range is maximal are free. And hence maximal. Yeah. The n limited allows us to form the restriction the restriction from minus infinity to n minus 1 closed, right closed. Because it's limited, we can see that S equals the range of this limit of this restricted function, which is the same as the range of the whole function with the same restriction, is a free R maximal set. Maximal free, sorry. Okay, and the less than 0 n shift invariance of S is almost seen from the self-embedding of range of F by the less than 0 n shift. I mean, the less than 0 n shift invariance of S in the sense of invariant maximality. Now, what we really want is less than one Z plus shift. So there's a trivial change because we're using N instead of Z plus. With invariant maximal choice, we like to use N instead of Z plus. That's just a minor point, but we do that. So we have to be a little bit careful then to work with S plus 1 as the critical point for S is 0. And we have the same endpoints now with Q minus infinity N and Qn. So we get exactly what we want, but only in the sense of this. From the free choice there, we get exactly what we want, maximal free set here, which is suitably invariant. We get that, but it's not quite the same because we're on a different space. We're in a space with no left endpoint. So this requires a technical fix. And so this requires that we start off with R adjusted by going to one higher dimension. We go to one higher dimension, and with the extra argument serving as a base, as a left endpoint. An artificial left endpoint. How about this? An artificial which is so we're going to get something stronger than we want, which is not surprising because artificial. We're going to get something stronger than we want because we already added one dimension, but then we just set that extra dimension to be extra coordinate to be 0 to match Q0. Yeah. Okay, this this establishes the reversal, and now we have the intriguing question. Going back to the statement, not that one, this one here. What can we use? Less than 0 N shift is a very simple function, of one-dimensional function. It's the identity on the negatives and +1 on the elements of N. What other functions can we use so that this statement is true? And when given a function that we use, when is this going to be independent? So these are questions of which we have a lot of partial information on it, and there's still some open questions certainly concerning this, and in fact, this is such a very, very simple. In fact, this is a Pressburger function. I mean, of this, basically the simplest kind, not even close to. It's not even using addition. It's just using. I'm not even using full addition. It's just using successor. So this is actually rather intriguing that very simple functions will give you this power. And the question is, what is a complete classification of the simple ones, or maybe even complete classification of more complicated ones, and so forth. One expects, for example, a decision procedure for all Pressburger functions that could be used for this statement, and less ambitious forms of that. But the decision procedure can't be given and it can't be both given and verified without large cardinals, because it has this special case. And also the actual decision procedure ought to be, very efficient and pretty easy to describe. That's what one expects. So that's ongoing research. All right. So I think that we're done with this, and next lecture, we'll start the reversals in lecture 7. Andreas?
Yes, great. So I will now stop the recording.